Hello everyone, my name is Laura Hensel and I'm a PhD student at the University of Glasgow, and today I'll be talking about the use of data-driven methods to generate psychologically valid face features for virtual agents, social face features. Virtual agents are becoming more and more important in our day-to-day life, be it in healthcare, education, or gaming settings. Now, the effectiveness of these agents, be it, for example, in increasing adherence to healthcare interventions or educational training, depends massively on these agents' social signaling capabilities. Now, by this, I mean how effectively they convey social messages to their human users. So this could be things like how happy they are, or their attractiveness, or things like their competence or trustworthiness. Now, we humans actually make this sort of judgment extremely quickly, and we make it all the time. So within psychology, there was a push actually to find the sort of fundamental dimensions along which we make social judgments. And the two main models that emerged from this are the dominance trustworthiness model by Alex Todorov and the competence warmth model by Susan Fisker. So these four traits are really boiling down hundreds of traits to really the fundamental traits that we judge others on. And they are extremely important for our daily interactions with each other. And so they should also be important for guiding the design of impactful social agents. Now, one very important source of social information is the human face. So if you look at this face, for example, you might immediately think it's kind of, yeah, it's trustworthy, not very dominant though. So for us, it's really easy to make these decisions and judgments, but to actually make a social agent look competent or warm or trustworthy, you need to know exactly what features in the face drive that perception. However, you run into a challenge there, that is that the face is extremely complex. So it comprises color, so complexion, but also 3D shape. So it's an extremely high-dimensional information space. Because of this, previous research has often focused on a few selected features, for example, the eye size, or the shape of the mouth, or the width of the face. There's also been some work trying or modeling the entire body for social traits. This work again faces the challenge that each modality that you add increases the information space that you have to model drastically. So again, you then have to pre-select a few features to concentrate on. Now this really drastically limits the amount of detail you can model. So when it comes to really nuanced perceptions of social traits, we're actually lacking quite a bit of information. This is why we focus here on the face, which is in and of itself already actually a massive information space. And this is especially true because we model both the 3D shape, so that's tens of thousands of shape vertices, and the 2D complexion, so that's millions of complexion pixels. And to do this, we use a novel method that is extremely well suited to modeling high-dimensional information spaces like this. And it's rooted in psychology, uses reverse correlation, and is directly based on human perception. And I go a little bit more now into how this method works. All right, so on each trial, we generate a random stimulus. We do this by sampling randomly sampling the variance, shape and complexion variance of a set of 402 real faces, which we describe in terms of 402 principal components. And these components essentially describe the identity-specific information of these faces. We combine this with the more common information, so this is the same across these faces, and that's age, sex, and ethnicity. So in our case, this would be faces between the ages of 18 and 35, male or female, of white Western European ethnicity. We do this for shape and complexion separately and combine for full stimulus. We then present the stimulus to our participants who rate it on a given trait, for example, from extremely dominant to extremely submissive. And importantly, each participant rates each face on each of the 4 traits. We do this over literally thousands and thousands of trials. And the beauty here is that we are not making any a priori decisions about what we think drives the perception of a given trait, what features are important to a given trait. But instead, the participants themselves get to continuously select the features which for them drive their perception of, for example, a dominant face. Now, after many such trials, we regress the stimulus information against the response for shape and complexion separately. And as you can see down here, we actually do this for each shape vertex separately, and also for each 2D complexion pixel in LAB color space separately. We then end up with an extremely complex and statistically robust 3D model of the shape and color information that drives the perception of a given social trait for that participant. So here, for example, extremely dominant and extremely submissive. And importantly, we do this per participant because on one hand, this means we can show replications across participants, but even more importantly, this means in the end, we can generate a variety of dominant faces, not just one dominant face, but we can actually, in theory, mimic 30 different dominant faces. So we increase the variance across these, generated faces, which is very important for things like realism, for example. Now, before I go into the results, I should say I will focus today on the results for male faces, just for time constraint reasons, really. Let's have a look then at two examples. So here we have very exaggerated, submissive and incompetent face, exaggerated so you can see the differences a little bit more clearly. And I'll play now a video so it'll go from submissive to dominant, and pay attention to the changes in the shape, but also in the complexion. So you can see quite drastic shape changes, but you can also see complexion changes, especially around sort of the nose region and the mouth region. Same for competent, incompetent, to competent, incompetent, and back. And if I pause here, you can already see here that actually dominant and competent look quite similar here. Now, this really comes back to some theoretical models that predict redundancies across the four traits. So dominant and competent are meant to be quite similar, and trustworthiness and warmth are meant to be quite similar. Now, we were then interested in, okay, well, if these traits are similar, what is it really that is common across them? Do they share features, these four traits? And if so, that would be very useful because it would allow us to very efficiently generate social avatars with a given trait. Because in essence, if we have a latent feature structure across the four traits, just manipulating those features will change the perception of all four social traits at the same time. So that's what we did. Let's have a look first at the shape results. So first of all, the shape here is described in terms of thousands of XYZ coordinates in space. You could also refer to this as up, down, the depth and width of the face. We'll focus here on up, down, and the depth. Again, for time reasons, we found quite small effects in the width. We then cross-correlate for each shape vertex separately the shape information across the four social trait dimensions to find any features that are significantly associated with the perception of all four social traits. So for example, the brow might be changing from incompetent to competent in the same way as it does from submissive to dominant, and so on. And we do find a set of latent features across all four traits, and that's what we see here. Now, darker colors here represent higher participant agreement. So what you can see really is that the features that really drive the perception of all those four traits are in the eyebrow region, a little bit around the nose, and the mouth and chin region. Now, these will, of course, then be expressed slightly differently in each trait. So we next want to look at weights that we would need to give each trait for these shared features to represent a given trait. And we do this by looking at the Euclidean distance to the average face which in our case would be male faces between the ages of 18 and 35, white Western, that we have in our database, so that our stimuli were based on. Red then refers to upward or protruding features, and blue refers to downward or flatter features. All right, let's have a look at competence. So you can see here the eyebrows in the up-down region, up-down dimension are blue, so that would be lowered eyebrows. In the depth dimension, they are red, so that would mean they were protruding. So we have lower protruding eyebrows. The chin, however, is red in both dimensions, so it's shorter and protruding. Comparing this to dominance, we see pretty much the same pattern, except the colors are overall more saturated, so we have more, these features are more exaggerated in dominance. Now, because of our linear modeling procedure, the opposite of each trait, so incompetence and submissive, would roughly be looking the opposite. So most importantly, they'd have sort of upward arching eyebrows, which when I change now to warm and trustworthy, you also see this red eyebrows in the up-down dimension, meaning they are sort of upward arching, baby-faced. We also have sort of upturned corners of the lips, and finally puffier cheeks. We then did the same thing for complexion. So again, we cross-correlated the complexion information across the 4 traits. Here we are focusing on information from the 5th spatial frequency band. So it's overall coarser information, which is why we'll show more overall face information. But you can see, again, the darker colors represent higher participant agreement. It's especially around the forehead, eyebrows, and here these folds around the nose and the chin. Now, color is represented here in terms of 3 color channels: lightness, red, green, and yellow, blue. Let's first look at lightness for competence. You can see that it's overall quite a dark complexion with highlights around the eyebrows and mouth region, and dominant looks quite similar. And the red, green, and yellow, blue dimension, we don't find as many similarities between competent and dominant as for shape. Now I want you to concentrate on the light dimension when I change now to trustworthiness and warmth. And you'll see that these traits both share an overall much lighter complexion if I switch between them. This time with dark contrasts around the eyebrows and again the mouth region as well. Warm and trustworthy are also quite similar in the red, green, and yellow, blue dimension, sort of reddish, yellowish foreheads and green, bluish lower parts of the face. Now, finally, traditionally, complexion is not often looked at in relation to social traits. We were interested in, well, okay, how important then is complexion? How important is it to consider complexion? To conclude, we use a psychology-based reverse correlation approach to model the 3D shape and 2D complexion of 4 key social trait dimensions. And we find a set of latent features, including the eyebrow arch, chin protrusion, and lightness. Well, you didn't see this, but we actually show that while shape is slightly more important, the combination of shape and complexion might drive perception above and beyond this. And finally, we anticipate that this approach can be used to model other modalities. We'll, for example, use it and have used it to model facial expressions of social traits, to really combine these features and then enhance the social signaling capabilities of virtual avatars. Thank you very much for your time. And if you want, please get in touch through Twitter or email.